Hi students, today is going to be your first lecture of the 8th week. And actually this topic, superconductivity, is going to be your last topic that you're going to learn for the first half of the semester. What is superconductivity? Now let's take a look at the word superconductors first. So there is a class of metals and compounds known as superconductors whose electrical resistance R decreases to almost zero below a certain temperature Tc called the critical temperature. And let's take a look at the graph. Here what we plot is the resistivity. And some people can plot R versus T, but you're gonna end up with the same shape. So rho is resistivity. And sometimes we can use R. R is resistance. So let's take a look at the normal metal first. At very high temperature or higher and higher temperature, the resistivity rho or the resistance R increases as the temperature goes higher, right? The curve is just like this. And at T, supposed to be 0 Kelvin here, due to all the normal metals, they still have impurity, right? So this one gives us the rho naught due to the impurity. This is rho naught due to its impurity. Okay. And why at high temperature, rho or R increases? You can think about like this. So assuming here, my purple dots are lattices, right? And at higher temperature, so let's see, electron wants to move from one side, right, to another side. So now I draw more lattices here. Or you can imagine yourself stay in a room, right, at one end of the room, and in that room you have boxing pillows hanging on the ceiling, a lot of them, like as array like this, right? And let's check every one of them, let's check it. So if you want to move, maybe you ask your friends, you have more electrons here, right? So you ask all your friends, okay, let's move from one side of the room, right, to another side of the room. So at higher temperature, the lattice is moving or vibrating, right? So more vibrating. It's the same like you shake the boxing pillows that hanging on the ceiling. So it will be the obstacle for electrons, right, to move from one side to another side, the same as like to move people or to run, people run from one side, right, to another side. It's the same thing. So that means what? The current will be smaller, right? The current is smaller. That means the conductivity, current, this is I, current is smaller. So C is the conductivity is smaller. So that means rho resistivity or resistance is higher. Okay, because at high temp, there are thermal vibrations of the lattice that prevent the movement or the flow of electrons from one end to another end. Because what? I is Q over T, right? So amount of charges per time. Okay, this is the current definition. So that's why it's like this. Okay. Now for superconductor, okay, things can happen like at high temp, but at a certain temperature we call critical temperature, there's a sharp right here that like all of a sudden the resistivity or the resistance of the matter reduce it to be zero. So it's just like fluid. I mean, like you don't lose any energy. There's gonna be a current forever through that metal. Okay. I show you the graph here. So this is critical temperatures for various superconductors. You see various of materials here. Seeing Al aluminum, Sn tin, Hg mercury, Pb lead, neodymium, and compound of neodymium like neodymium tin, neodymium germanium. And the compound of copper, for example, yttrium, barium, copper oxide, bismuth, strontium, calcium, copper oxide, and thallium, barium, calcium, copper oxide, right? And this is the form of the mercury, barium, calcium, copper oxide. And on this side, you see critical temperature. So it's gonna be higher and higher and higher, right? This is the first discovery of the superconductor, which I will explain you very soon. But let's take a look at this. The approach is like they are researchers. They want to get higher and higher critical temperature for the material that will be more applicable to real life, right? I mean, we need room temperature to operate, okay? Okay, I almost forgot to tell you what the graph of rho versus T for semiconductor. So you have rho or R versus T for semiconductor. Since semiconductor, the way they explain is like using the energy diagram. They have valence band And above here, they have conduction band. So when electrons that are in valence band got energy or like absorbed energy, either in the form of photon, right? Photon has the energy h mu, right? Or hf or h bar omega, or it can be with temperature, right? So these electrons got energy and they can jump up to conduction bands. So you will assume that if T is higher, right? T is higher, the current or the conductivity will be what? Will be higher. So rho would be smaller. Rho or R would be smaller. So the graph would look like this. Something like that. Okay. So that's the different. So they use different concepts to explain the curve or the graph of rho versus T for metal and for semiconductor. Okay, here is a table called transition temperatures of well-known superconductors, including boiling point of liquid nitrogen, here a liquid hydrogen, and right here is going to be boiling point of liquid helium, which doesn't show up right here. This is various types of materials in the form of copper oxide, right? Especially this one, yttrium. Barium copper oxide is the famous one. When I was a PhD student, long time ago, I used to help a postdoc, actually from another group. She was like making YBCO powder and make it as the superconductor. So that was fun to work with her. And this, for example, YBCO got the critical temperature equals to 90 Kelvin. So that is higher, right, than the boiling point of liquid nitrogen. So that means when you put the YBCO, right, in the liquid nitrogen, the YBCO behaves like superconductor. Okay, now go down to the iron base here, right here. The critical temperature is lower too. And here you have to submerge in the liquid hydrogen to get the superconducting phenomena. And this last four is form of the metallic or somehow compound of metallic. This has to be like very, very low. So you have to deal with the liquid helium to get the superconductivity phenomena. Okay. There's another developing that how people discover the superconductors, critical temperature versus years. Okay. In the beginning, this is of course they did experiment only for metals, some sort of metals or the metals compounds, neodymium compounds, and around 1990 they start doing the copper base here. As you can see, I already read these names out, some of the names out for you here, but I want you to emphasize right here. So this is mercury, calcium, barium, copper oxide, right? But the interesting thing is that if you put higher and higher pressure, so this is like a mechanical higher pressure, it will increase the critical temperature by like could be 20 Kelvin, which is quite a lot. So this is quite amazing technique to make one material to become even more like superconductor with more critical temperature values, okay? And MgB2, this is the new material discovered in 2001. This one is quite new, but they didn't discover other form of like Mg, you know, or even like boron, but this is quite interesting if you wanna take a look at that. And in 2010, this is form of iron-based pump, and they will still like research developing. So the dotted line is the boiling point of liquid nitrogen, about 77 Kelvin here. Okay. So everything that above here, right? If T, this is T experiment, let's say, right? T experiment is less than Tc, so this critical temperature Tc. So the matters will become superconductor. So above this, if you do experiment under the liquid nitrogen, they're gonna perform superconducting properties, okay, but not here below, okay. Here's is another like a periodic table, but they color with different codes, blue and green. Blue, all these elements can act like superconductive at ambient pressure, but the green elements will do it only under high pressure. Okay, this graph, actually I already explained in the first slide, but I will emphasize right here again. Remember here, rho 0. So this is due to impurity in the metals, okay, that cause like some resistivity that is not 0. But if you zoom in here, this is almost like flat, okay. Here is the history of superconductor discovery. The scientist who discovered, his name is Ernest, and he got the Nobel Prize in Physics in 1913. in the topic of investigation into properties of substance at low temperature, leading amongst other things to preparation of liquid helium. Thanks to discovery of helium liquefier, that's how he do very many experiments. So he cooled many metals like gold, platinum, and later he cooled mercury, and then he measured the resistance. Okay, resistance versus temperature. Okay, so this how he did experiment 1911 in October. So this experiment shows the superconducting transition at 4.2 Kelvin. Okay, within 0.01 Kelvin, the resistance jumps from unmeasurable small, less than 10 to the minus 6 ohm to 0.1 ohm. So this is quite small here that he observed. He wrote it down here, 10 to the minus 5 ohm here. So approximately like 0. So this one, is a picture of the lab, his lab, and the picture of him on the right, and this is his technician. Okay, let's take a look at another history. On the left side is a picture of Walter Meissner, and on the right side is a picture of Robert Ochsfeld. So these two scientists discovered that superconducting material will repel a magnetic field. Remember last time we learned that diamagnet repel, right? Repel a magnet, okay? So we'll talk about that later. A magnet moving by a conductor induces current in the conductor. This phenomenon is known as Meissner effect, and so strong that a magnet can actually be levitated over a superconductive material. I will show you a video very soon. Okay, let's take a look at another history. This is called BSC theory, okay? The scientists who discover this phenomena, BCS, sorry, not BSC, BCS. B is from last name of the first guy, John Burden. This is B here. And C is from Leon Neil Cooper. This is C. So look at this, Cooper. We'll use this word again. And John Robert Schaeffer. So this is S here. BCS theory. So they got award in Nobel Prize in Physics in 1972 for their jointly developed theory of superconductivity. And this is again called BCS theory. So let's explain this diagram. Here is like an ion core, okay? Ion core. And remember the way that we think about current is like, okay, amount of charges, in this case, like electrons moving. So the current move in an opposite way because electrons have negative charges and current supposed to be positive. But anyway, right here, what happened? The theory said, oh, look, this electron, right? If you apply an electric field, so let's say apply electric field, this is 0, this is positive, so electric field go this way. Okay, like that. And what happened right here? What happened right here? So as electrons move this way, right? So they try to attract all the ion lattice here close to them because they are in opposite charges. Okay, they are in opposite charges. But the next electron will become attracted to the lattice or the ion cores that are formed that they got closer. So if I maybe so this is like this, right? So this is like, let's say before electron move, but once electrons move, get closer to this group, right? Let's say electron, let's make it blue like this, right here, okay? Electron right here. I just said the next electron, I mean, they don't feel like they want to repel from this electron, but they feel that, oh, look, I mean, this is large groups of positive ions. So let's say, so they try to like attract this way, okay? Let's take a look at the magnitude. So the lattice spacing between ion core, let's say 0.1 to 0.4 nanometer right here. And the Cooper pair of electrons, Cooper comes from this guy, Leon Neil Cooper, is much larger than the lattice spacing, 100 nanometer. So we call it phonon interaction here. And so once so we said this electron and this electron, we call it Cooper pairs. So two electrons having equal and opposite spin. So one, let's say opposite up, another one. So let's use another color, let's say. One, let's say opposite up, and another one will be opposite down. Equal and opposite spin and momentum. And when they form like this, they are no longer fermions, but they behave like bosons, which become like a more fluid, like a fluid bosons, because they don't act like fermion anymore. So some of you maybe want to review these words, fermion and bosons. Fermions has been like a half integers, like 1/2, 3/2, but boson have like complete spin integers, like a 1, 2, something like that. So now we have 2 electrons that pair up, and the behavior becomes like boson. Okay, so this one maybe you can review by yourself a little bit here. Okay. The Meissner effect is a phenomenon that magnetic fields are expelled from the interior of superconductor. So let's read this one. According to Ohm's law, the resistance of a conductor is given by R is delta V over I, where delta V is the potential difference across the conductor, and I is the current in the conductor. Because of the potential difference, delta V is proportional to the electric field inside of the conductor. The electric field is proportional to the resistance of the conductor. Therefore, because R is 0, right, for a superconductor below the critical temperature, so electric field, right, so R is 0, delta V is going to be 0, and delta V is proportional to E field. So it has to be 0 right here, right? Has to be 0. So from Faraday's law of induction, express that integral E ds is the change of flux, magnetic flux. So the magnetic flux, this is the B is flux B by the by area. So the line integral of electric field around any loop, closed loop, is equal to negative rate of the change in magnetic flux by B through the loop. Because E is 0 everywhere inside of the superconductor, the integral over any closed path inside of the superconductor is 0. So that means this is 0 and this side has to be 0. This tells us that the magnetic flux in the superconductor cannot change, right? Cannot change. So from this information, we conclude that from this information, a B must remain constant inside the superconductor. Okay, so this is an experiment of the Meissner effect. To observe the Meissner effect, we have superconductor. This is YBCO, that's the form to make like powder and grind it and then make it to be like a tablet. And then you put the liquid nitrogen in, and then you place the small permanent magnet. So this has to be very light, okay, to observe this phenomenon. So it said that the superconductor completely expelled the magnetic field and behave as perfect diamagnet. Remember diamagnet? So let's review quick diamagnet here. So assume you have 2 electrons pair up, right? Diamagnet, you don't have unpaired electrons. So all of it has to be paired up. So when pair up one, let's say this is I, but electron going in an opposite way. So when I is here, the mu would be in this direction. So this is the magnetic dipole moment. So it looks like you have a magnet here. So this pole is N, this pole is S, right? And another loop, another electron. So you have another electron here. So I is right here. So you have another mu this way, right? Look like you have N and S here. So notice that like this cancel out, right? But why they repel with a magnet, okay? So you have to review the Faraday's law, which is, I already gave it to you, right? Integral E dot ds is minus d flux B by dt, and review the Lenz's law, okay? So this one's supposed to be canceled out, right? But for example, if you bring the magnetic field, a magnet, okay, let's say a magnet or magnetic field in, so let's make it the north. So the north, you know that the magnetic field go out, right? So let's say something like that, okay? And now you're moving in here. So this guy will have to do somehow that, so if you moving the magnet in, right, the flux will be what? Higher and higher in the loop, right? In this loop, okay? So this, let's say the first one, need to somehow that produce the magnetic field that oppose in direction to the blue line, right? Because the blue line is moving in, that means like, okay, you have increasing in B field. So the system need to do something that prevent the increasing of B field. So they have to create the B field, right? In an opposite way like that, okay? So that means like I will be higher. So let's say if I draw again, I draw that, okay. After that, I draw right here. Or maybe right here. After that, the first one, it will become larger mu, okay? So this is mu. Let's call it mu1, okay? And another one would be, let's say smaller, second one, mu2, okay? So look at this. So these two no longer cancel each other like this, right? Like before we put the magnet. So this one gives us the delta, which is like mu1 minus mu2, let's say, right? Like that, okay? So give us somehow in this direction. So it's just like a magnet. So this is N, no, this is S, like that, magnet like this. So that's, look at the direction. So the blue direction and the what? And the orange direction here. So you have like N pole and N pole. So that's why the diamagnet repels the magnet this way. So let's explain in equations way. Here is the superconductor. When T is larger than critical temperature, you have B field, external B field. Penetrate through the superconductor. When temperature is less than Tc, inside of this B field is gonna be 0. So Meissner effect is the exclusion of magnetic flux from the superconductor. So this is due to the screening current on superconductor surface that generate the internal field mu naught M. So this is the internal field inside of this, and different direction or opposite to applied field mu naught. Okay, so B is gonna be the total after subtract these two. So this is from inside. Oh, sorry, mu naught M is from inside and mu naught H is from outside. And when they cancel out, so B has to be 0. So Meissner effect if H is minus M. Okay, and some people think about that when T is less than Tc, right? There is the, we call it surface current. Okay, so if you use the right hand rule here, you will see that the B field inside of the superconductor point opposite. Okay, so that means the surface current direction has to go around counterclockwise this loop. Okay. Okay. This one come back to Cooper pair again, but actually I already mentioned that to you. But let's emphasize this a little bit more. So here you see the word bosons and fermions. Fermions are particles with half integral spins, and bosons are integral spins. Fermions cannot be in the same state. Okay. According to the Pauli exclusion, but boson doesn't have to obey the Pauli exclusion principle. So at very low temperature, it would be possible for all four bosons in a collection of such particles to be in the lowest quantum state. So as a result, the entire collection of Cooper pairs in the metal is described by a single wave function. Okay. Here again, you will see that if we place the orientation of the magnet is above, and the plate or the disc down here is superconductor, could be YBCO. You will see that there's going to be a direction of the surface current, right, that will produce the B field that opposed. Look at this, right here is up, right? So down here, so when you do the right hand rule, the current will be clockwise. Yeah, so that the B field that created from the current that goes clockwise will be in opposite direction of the blue here, because this go to the south. And in this case, there are two regions because N is go like that, right? So when N is go like this, so let's say like that, right? So this is like go this way, downward. So the current has to go like counterclockwise, okay? And B field go up, okay? And here go out, right? Because this is S pole. Sorry, go in. So it's like go up. This is up direction. So the surface current on this region has to go clockwise. So this is clockwise. This is counterclockwise direction. Okay, now I'm talking about type 1 and type 2 superconductor. And here we plot magnetization versus applied magnetic field for type 1 and type 2. Okay, for type 1, you see these two graphs. So this M versus H, this is H versus T. So right here, if you see minus M, right, that means it's diamagnet. Remember that? And the H applied magnetic field has to be not much, right? So it has to be below a certain critical HC right here. And so this is critical, and then you use this one to plot versus T. So if H below HC and T below TC, that material acts like superconductor. But if T is larger than TC and H is larger than HC, that material is become a normal metal again, or just a normal property. And here type 2, you have like separations. You have HC1 and HC2, and are more than HC1 but less than HC2. There's gonna be something that like still go through the material. So there's flux lines present in the material. So still like some flux. Look at this. So H is between HC1 and HC2, and but T still need to be like lower than TC here. So this is the flux line present, and after that it's still normal. And for Meissner effect has to be H is less than HC1 and T is less than TC. Okay, another phenomena that I want to talk is called Josephson current. I'm not gonna go to the detail, but I just want you to see this diagram. So you have a material A, material B, right? And you have an insulator. It's just like a sandwiches, right? Sandwich of metals in between the insulator. In classical, you would think like, okay, no way that you will see any current go through this circuit. But if you really do this, you will see there's a signal of the current passing through it. And why is that? I mean, you have to think of the classical way. Okay, imagine this is classic quantum way, sorry. This is classical. You throw a ball to the wall. No way that the wall will penetrate through the wall and being seen on the other side here. No way, right? It's like classical view. But in quantum, you think of particles as wave function. Okay, wave function. So wave function, that means like there's gonna be probabilities that outside of the metal, okay? And this is gonna be another possibility of seeing another particle outside of the metal. So that means some of these will show. So that's gonna be just like a cartoon picture that I'm gonna just draw. So this is, for example, wave function, right? And then maybe could fall down like that. Then on the other side, another wave function, let's say, and fall down like that. So wave function square, there is wave function. And wave function square is like a probability of observing that particle, right, in that region, for example. So this sum of the pink and the red, you know, still give you something that, let's see, maybe green, use green. Still something, probability of seeing something. Okay, so this is like a quantum view. So you will see that there will be a current flowing from this metal to this metal, even though you have an insulator here. But this metal has to be superconductor at that time, okay? Not normal. Three scientists are observed this phenomena effect. Leo, Isaki, Eva, Guyver, Brian, David, Josephson, and the one that actually they live in different places, but the one that they think they contribute more is Josephson. So that guy got 1/2 of prize, and he's from United Kingdom and University of Cambridge, England. And that's why the phenomena called Josephson effect or tunneling, Josephson tunneling. Okay. I try to stop share first, and maybe I will show you the Meissner effect here. Do you see that the tiny magnet is lift up? And even like they can spin it. So they pour liquid nitrogen. The black disk is YBCO. Isn't it cool? Okay. Look at this, even cooler. Okay, that's done. Okay, thank you for listening. I will soon give you the take-home exam and we'll talk about that later. Okay, see you, bye.